So we have test 2 tomorrow, okay, and I think I kind of listed what you need to know for or what kind of problems you should expect, okay. I've also modified the worksheet number 11 on Canvas just to clearly cut off at where you should stop studying for test number 2. So if you printed out the file early or yesterday or something, you might want to print out it again, okay, especially the last couple of pages. So the first 3 problems are the same. I've slightly modified problem number 4 so that it kind of it's a better problem for you to practice for the test. And it's up to there that you're going to cover for test number 2. So while students are slowly getting in, so problems 1, 2, 3 are the same as earlier. Problem 4 is slightly modified. I just added this part there. Okay. So if you have an older file, just modify it. And that's up to where tomorrow's test will cover. So I'll try to keep the section 3.11 question pretty simple and easy, okay, because pushing it really close to the test. I don't want to push it next week and then it'll be a weekend for you to study. Okay, that's too much. So all right, so this is the list of topics for test number 2, double integrals by reversing the order. Okay, polar coordinates. That was on quiz number 3 as well. The only brand new topics are these 3 here. Okay, these 2 were on worksheet number 10, and you should be able to decide whether cylindrical coordinates or spherical coordinates is appropriate for each problem. That's the only thing you have to be just careful in deciding before you start doing and wasting a lot of time. Okay? And then the surface area problem that we are going to do today. So the problems 3 and 4, that's what is remaining. Okay. All right, so that's where we are. Do you have any questions before we start? Then all that information is on the worksheet. Okay, so there's nothing that I just removed and you are not able to see it again. Okay. All right, so let's try to do the surface area problem. So worksheet number 11, number 3. I should warn you that this is a problem which is a little bit lengthy because of the way it is set up. So I'll write the parametric form, which is given in the question, and let me see if you understand this or not. So R of UV equal to capital R sine U sine V, capital R sine U sine V, and capital R cosine U. Where U goes from 0 to pi, V goes from 0 to 2 pi. The question is to find the area of the surface parameterized by this particular form. Okay, so this is your X, this is your Y, this is your Z. Find the surface area. And since it's a summer session, I know things happen fast, but the good thing is that you have seen things pretty recently. Okay, looking at these 3 components of this R vector, can you tell me what does this remind you of? The sine, cosine, sine, sine, cosine thing. What kind of a? It's a sphere. Okay, it's just a parametric form for a sphere of radius R. Okay. That's what you're trying to find here, though it looks crazy because of all these R, sine U, sine V notations. Okay. Do you remember what the formula for the area of a sphere was? From your middle school or high school? Anybody online, do you remember? No? 4 pi r square. Okay. It's the same as the area of a cylinder of the same height as the diameter of the sphere. Okay, that's how you should think about it. 4 pi r square. So let's try try and see if you get that result by doing this crazy computation. So let's start with the partial derivative of r with respect to u. I should warn you that this example is going to be a little bit lengthy, so make some room for yourself, okay, in terms of how much you want to write and so on. Partial ru would be r cosine u cosine v, okay, because the derivative is only for the u term. Sine of u becomes cosine u. The v term remains the same. R cosine u sine v, and negative r sine u. That's a derivative of partial derivative of little r with respect to u. Little r with respect to v would be negative r sine u cosine v. What did I say? Negative r sine u sine v. R sine u cosine v. What is the last one? What is the partial derivative of the third component with respect to v? 0. Okay. There is no u there, so it's 0. So when the question is to find the surface area, those are the first two things you should find. Okay, the general partial derivatives of the surface with respect to u and v. Now we have to write this awful determinant, which is going to compute the cross product. Let me make some room here. So Ru cross Rv. So I'm just going to write it component wise downwards so that I know how much space I need for each term. Okay. So the first component here would be R cosine u cosine v, and the first component of the third term is negative r sine u sine v. That's the first column. The second column is j r cosine u sine v r sine u cosine v. And k negative r sine u 0. I have taught in classrooms with much smaller chalkboards and I've struggled to write that there. So this one, at least I'm lucky to have this much space. All right, so let's expand it along the first row. It's going to be I times 0 minus negative r square. That's going to be positive r square. Sine square u cosine v. That's 0 minus that. Minus j because of the alternating sign of the determinant times multiply those two, first and the third. That's a 0 minus the product of these two, which is going to be so I have a double negative there. That's going to be positive r square sine square u sine v. Let me know if I'm missing any sign or anything. So it's going to be minus j for the middle term, 0 minus Yeah, that's a plus term because it's 0 minus positive. So you have a double negative that's positive. Okay. Though when you compute the magnitude, it won't matter, but let's do it correctly. Plus k times. Now comes a slightly insane term, which actually when you simplify it, won't be too bad. That's going to be r square sine cosine square v. Okay. R square sine u cosine u cosine square v minus negative, that's going to be positive. That positive is critical. Okay. Plus r square sine u cosine u sine square v. All right. Right now it looks kind of crazy. Okay. Let's try to simplify this block here. Okay. This last term is r square sine u cosine u times cosine square v plus sine square v. Whenever you see this combination, you know life is good. What is that? 1. Okay. So something that looked pretty awful suddenly just collapses into this one term, r square sine u cosine u. Okay. So this vector, if you just write as components, would be r square sine square u cosine v, r square sine square u sine v, and r square sine u cosine u. That is the vector which represents the cross product of those two vectors on the surface. Okay. We have to find its magnitude, so we need to do something to make our life easy. What you can see here is that this r square, and there is a sine u that is common to all the terms. Okay. So it's r square sine u times, just to make it easier to compute later. Then what remains is sine u cosine v, sine u sine v, and cosine of u. You could keep it inside and do it, but it will get unnecessarily long and confusing. Okay. All right, now we have to find its magnitude, which means you have to square and take its square root. Okay. Square and add the components, take the square root. So the magnitude of Ru cross Rv is well, when you square and take the square root, this term is not going to change. Okay. Because you're going to square, take the square root. The r square sine u is still going to be out there. It's just the inner things that we need to change. It's going to be sine square u cosine square v plus sine square u sine square v plus cosine square u. Okay, so the magnitude of a vector is the sum of the components, square, add them together. Okay. Now you will see some nice things happening. Okay. Look at the first two terms, pull out the sine square u, and you have cosine square v plus sine square v. Happy again. Why is that? That's 1. Okay. So that becomes r square sine u times the square root of this sine square u plus cosine square u. Wow. What is that? 1 again. Because whether you call it as u or v, as long as the same letter here and here, that's 1. Okay. That's r square sine u. You'd have never thought that's going to simplify into this thing. Okay. Remember, we are trying to find the surface area of a sphere. Okay. Have you seen a term like this somewhere in the spherical coordinates? If you look at the dv thing, right? Yeah. So look at the dv in spherical coordinates. It's rho square sine phi. Okay, that's your rho square. The phi is the angle that's going from 0 to pi in this case. Okay. So this is not a completely unfamiliar term for us. This is something that we have seen, okay, but it has actually come to us in an algebraic way. Okay. We derived it based on a picture that is a geometric way of looking at it. It's also the same thing algebraically. That's why math is so strong. You cannot really beat it from one side or the other. It has to agree from all sides. All right, so that is the magnitude of the cross product. Now you can integrate it from the limits that is given in the question. Okay, so the area is the double integral of that term, r square sine u. Okay, and the limits of integration are in the question. U goes from 0 to pi, and v goes from 0 to 2 pi, right? So when you do this, my hope is that you'll get 4 pi r square. R square is a constant, so you can write this as r square times 0 to 2 pi dv and 0 to pi sine of u du. Integral of sine is negative cosine, so this part is 2 pi r square. Times negative cosine u from 0 to pi. That negative is important because we don't want a negative surface area. So it's negative of cosine pi, which is negative, -1, that's positive 1, minus negative cosine of 0 is 1. Okay, so this term is 2. So this is equal to 4 pi r square. So whatever you probably saw earlier and forgot, or the surface area of a sphere of radius r is 4 pi r square. But that's probably a very long problem because of all these terms. Okay, I will never ask you to do something as complicated as this. The problem with these kinds of exercises is that you should be very lucky to get a nice thing to integrate at the end. Okay, usually if you do RU cross RV, take its magnitude, you end up with a pretty unsavory term all the time. Okay, so there are very few problems that can be done nicely using this. One of them is in your, other than this one, okay, one of them is in your worksheet. A few others are in the old exams, so try to do those. Okay, and then there'll be one tomorrow. So those are the only ones that works nicely. Okay. So let's do the next one now. Can you do the next one yourself if you don't have any questions about this? So break it up into 3 parts. Okay. Find RU and RV. Then find RU cross RV. Then find its magnitude. And then find the double integral. If you just break it down into these steps, I think it should be reasonably straightforward to do this problem. Okay, don't just do this one all at once. So take number 4, which is a modified problem. Okay. All right, let me slowly start doing this. Okay. So I think the parametric representation was R of u v equal to u cosine v again. This is your x, y, and z. And if you kind of look carefully, okay, the surface is given by z equal to 16 minus x square minus y square. That is the surface. Okay. So it's actually a paraboloid that is facing down, and the once again our friendly terms cosine square and sine square add up to be 1, so it works out nicely. Okay. Parametrization is an art. So if you don't start with the right parametrization, you will end up with all kinds of nasty integrals. Okay, this one works out nicely. So it's unfair to ask students to come up with a nice parametrization. I won't do that. Okay, that is cruel to do it on the next day test or something. So I will always give you the parametric form. What I want you to do is those 3 steps there. Okay. So my promise to you is I won't put you in a terrible situation tomorrow. But if you don't know how to find partial derivatives, I don't know what to do. All right, let's see. Partial RU is cosine V, sine V, negative 2u. Let me know if you disagree with any of these. Okay. Or V is negative u sine V, u cosine V, and 0. Okay. Go to write negative 2u, 0. All right. Then, so that was my step 1 there. Find RU and RV. Find the cross product RU cross RV. V So the mistakes that you should not make is to first, and don't write it as a scalar. Okay, this is a vector in R3. So this is the I component is going to be 2u square cosine V, because it's 0 minus negative, right? Minus j times, remember that positive, negative, positive, minus j times 2u square sine V. So it's again, that's a positive. That's a negative, and then you have 0 minus 2u square sine V. I should just write it down instead of doing mental math. So it's 0 minus that, that's going to be positive, yes. And the k component is where nice things start to happen. That's going to be u cosine square V plus u sine square V. One of the sad things that happen on tests, students make it a minus here. Okay, that is one of the worst things you could do, because the whole point is that the cosine square and sine square should add up to 1. Okay, and this term should just become a u. If that remains as cosine square minus sine square, the integration becomes all wild. Okay. Yeah.
If it was negative, though, couldn't it just be negative u? And when you keep it magnitude?
The magnitude is okay. I mean, this one, no. If both were negative, you're okay. If one of them is negative, you have a problem. Then you're left with this thing, cosine square V minus sine square V. Unfortunately, yeah, you don't want to deal with that guy, especially on a test. No, you could do it, but not tomorrow. Let's try to keep things nice and easy here. All right, so the components in a clean way are 2u square cosine V, 2u square sine V, and u. Okay. So without prompting, you should be able to identify the cosine square plus sine square equal to one thing. Okay. All right, so that was step number 2, part A. Now we need to find its magnitude. Okay. Magnitude of RU cross RV is square root of 4u to the 4 sine square v plus 4u to the 4 sine square v plus u square. Yeah. You could factor out the u first. I mean, all the algebraic options are still in front of you, so you could but that might actually avoid a possible mistake later. Yep. Yeah. So these again, I love doing this because sine square plus sine square is 1. So it gives you the square root of 4u to the 4 plus u square. Okay. I've asked similar questions in past exams. Okay. Here is a common thing that students do. They see this term and the next thing, you know what happens? Can you predict what they would write this equal to? You don't want to even think about it. No. 2u square plus u. Is that right? No. I know it's very tempting. If this was a 5, maybe they wouldn't have done it. The 4 is just, too good to be true, right? So just leave it there, okay? And you could factor out a u square. And that's what he said earlier. You could have factored out the u earlier and kept it out. Or you could just do it here. U square times 4u square plus 1. And the square root of u square is u. Okay, so u times the square root of 4u square plus 1. So it's a small algebraic adjustment you have to do there. That's also a critical part for your integration later. So that is this part. All right, now let's do the integral. So the surface area would be the double integral. Can you remind me the limits, please? Pi or 2 pi? U times the square root of 4u square plus 1. And these were for v. V. Oh, okay, so v first, then u, if you write in that order. Of course, the v part will separate out because that is independent of u. So it's going to be 2 pi times the integral from 0 to 4 of u times the square root of 4u square plus 1 du. Okay. Once again, stay away from unnecessary trouble. This is not 2u plus 1. Okay. Sometimes I'm even scared to write it because students think that it's true. So. Okay. How do you do that though? Without any algebraic stunt, what do you do? Yeah. U substitution for a u term. Surprising. What is not surprising is, so you can use some other letter, right? W equal to 4u square plus 1. Just to avoid going crazy. All right, so dw is 8u du, 1/8 dw is u du. So the 2 pi is still out there, so it's 2 pi over 8. Let's just forget about the limits for now. That's going to be the square root of w dw. Okay, almost done. Let's pi over 4. W to the 3 half over 3 half, that is 2/3. And W is 4u square plus 1 to the power of 3 half. Okay, don't forget the exponent. I know it's a lot of things going on there. W to 3 half, that's 4u square plus 1, 3 half. And between the limits of 0 to 4. That's pi over 6 times, plug in the 4, that's going to be 16 plus 1, 17 to the power of 3 half, which I'm not interested in knowing what it is. Minus, when you plug in 0 here, that's not a 0, okay, minus 1 to the power of 3 half. That is 1, okay. 14 to the power of 3 half is almost 64, but not quite. 17 to 3. So that is as difficult as it can get tomorrow on this question, okay, or use substitution if you don't do anything funny, okay. But it will be even easier than this. All right, so I hope all of you are comfortable with that. Okay, so up to here for tomorrow's test. Okay, so there are, I think, 2 or 3 questions in the homework which I have recommended, which are not too insane on that worksheet. And also from the old final exams, just skip the 2019 spring exam question. It uses a slightly different version of this, which I'll do, but I won't ask you on the test. So you can skip that part, but I think maybe 1 or 2 other final exams have a question based on this, which might be useful. Okay, so just do those. As I said, there are not a lot of questions out there. So one of these kind of flipped over or something. All right. So any questions about that part? Is it 17 or 6? Oh, is it 65? Really? Yes, it is, right? 4 square is 16, 16 times 4, 64 plus 1, 65. Yes, you're right. 65 to the 3. Thank you. All right. Any questions about this example? So there's a small part of this section which I'm not planning to cover for the test, but the idea is this. Okay. If you are given the surface z equal f of x, y, let me just make sure that you up to here for so given a surface z equal to f of x, y, and if you want to find its surface area, do we really have to do this parameterization and then get the surface area, or can we just use the given letters itself? Okay. So do we have to parameterize using u and v all the time? And it's not something that you would expect you should know, right? If you find the surface area of something, this is not your automatic thought, right? Somebody has to force you into doing it. But is there a way to do it without that parametric process? There is. It's actually kind of a cheating process, okay, but it works. So if you write your r of x, y as x, y, and f of x, y. So in a way, you are just using the given letters itself. I'm not using u or v. Okay. So the x coordinate is x, y coordinate is y. The z is f of x, y. Yeah. So in a way, I'm doing the same thing. Find the partial derivative of r with respect to x. It's going to be 1. Partial of y is 0. The partial derivative of f is just partial fx. Okay. We don't know what that is because that depends on the function. Similarly, partial f or partial r with respect to y. Again, these are vectors because they have components. That will be 0, 1, partial fy. We do the same process. Take the cross product of those two vectors. Okay. Rx cross Ry. That's I, J, K. One, 0, partial fx, and 0, 1, partial fy. So I'm not really doing anything completely new in a conceptual way. All I'm doing is just sticking with my original variables x and y instead of using a new parametric form. So this vector would be, well, the first one would be 0 minus fx, that's negative fx. The second component is negative, that's going to be just 1 times fy, so it's negative fy. Okay, because they are sitting in the positive orientation. The k component is, well, it looks like 0, it's not. Okay, 1 times 1 minus 0 times 0, that's 1. Now, if you find its magnitude, Rx cross Ry, those negatives are not going to bother us anymore. So it's going to be the square root of fx square plus fy square plus 1. So if you integrate this term in terms of x and y, you will get the surface area. Okay. Now there is no guarantee that it's going to look nice, but the surface area would be the double integral of the magnitude of Rx cross Ry, which is this formula here. Okay. Partial fx square plus partial fy square plus 1 dx dy or dy dx, that depends on how you want to do it, over the surface that is given in the question. This works. Once again, the only concern is whether this is an integration that you want to do or not. Okay, it may not come out nice, but that is not our fault. Okay. So this is the part that I'm not expecting you to study for the test, but it's a very useful shortcut if you are given the surface in terms of x and y, and if you don't want to bother about other things. Does that look similar to something you've already seen in calculus 1? Yeah. Yeah, it looks like arc length, doesn't it? So that's not a coincidence. If you look at the arc length formula for the length of any curve, okay, you would get the integral from a to b, the square root of f prime of x square plus 1 dx there. Yeah. So look at how similar they are. You're looking at, instead of looking at the length of something, look at the area of something on the surface and adding it up. Okay. This was obtained by taking a small chunk here, taking that length as f prime of x times delta x here. Okay. That is how we obtained this, right? So these things are related if you look closely. Okay. All these are just higher dimensional counterparts of different things. Again, the tool that connects all these things, even if these are geometric things, is algebra. Okay, if you have the algebraic tools to do these things, everything is possible. Okay, that's what it shows here, because none of these things were based on any pictures. We all did all these things based on simple algebraic steps. All right, so let's do an example just to finish off that section officially. that is what I have in the worksheet as the last problem. And don't worry, this formula won't come back later to bite you, so it's okay to kind of see this and kind of move on. Okay. Where is it? Worksheet. So problem number 5, I think. So to go past the shortlist for test number 2, okay, you'll reach problem 5. And I've clearly mentioned there, I don't expect you to be responsible for that for tomorrow's test. Okay, so take it easy. 5, find the area of the part of this y square minus x square is some kind of a saddle shape. Okay. And that is lying above the region. So there is a circular region which is kind of between two circular boundaries of radius 1 and 2. Okay, that is what is given there. 1 less than or equal to x square plus y square less than or equal to 4. That will help you fix the boundaries of where we need, because this just extends from negative infinity to infinity. Okay. We need to stop it somewhere, and the stopping place is using this annular region. So what is the area of the surface which is directly above this shaded part here? Okay. So you can see there is no parametric form given here. You could sit down and try to parameterize it. Okay. As I said, that takes some experience because you have to do it precisely according to what is given in this problem. Okay. So there are multiple things to consider there. And that's where you could just bypass that and use this one. Okay. This is your f of xy. You're finding the area under that particular surface in this particular domain. Okay. F of xy is y square minus x square. Partial fx is negative 2x. Partial fy is 2y. Don't forget you to square these things. Okay, so partial fx square would be 4x square. Partial fy square would be 4y square. So this is not a parametric representation at all. We are just doing it in the original xy coordinates. Okay. So the area is double integral of this square root of fx square plus fy square plus 1 dA. Okay. A lot of students, they kind of forget that this 1 was there. Okay. That 1 came from the k component of the cross product here. So I know it looks kind of uneven when you write it. There is an fx as an fy, and then there's 1. Okay. And that's equal to the double integral of, when you square it, the negative goes away, 4x square plus 4y square plus 1 square root dA. We are going to integrate this over the region R, which is between these two circular boundaries here. Okay, this is your region R. Okay. Now, I think all of you have got some experience with these kinds of problems. Okay, looking at that region and looking at this particular term here, what would you suggest as a nice way to do this integral? What coordinates? It's a double integral. Okay, so don't polar coordinates. So because it's circular, you have got 4x squared plus 4y square. Okay, use polar coordinates. So either way, if you were to parameterize it properly, you would have gotten the same integral. Okay, but without parameterizing, you have to use polar coordinates. So they all kind of agree. Okay. What are the limits of r and theta here for this region? All right. 1 and 2. Right? So this is r equal to 1 and r equal to 2. So use polar coordinates with 0 less than or equal to r, 0 less than or equal to theta less than 2 pi, and 1 less than or equal to r less than or equal to 2. Okay, and x squared plus y square is r square, so it's going to be 4r square here, and this is that, or maybe not. Okay. So don't cause any troubles for yourself tomorrow. Okay, RD theta. Okay, let's do the integral now. That's going to be 0 to 2 pi d theta and 1 to 2 square root of 4r squared plus 1 r dr. I don't know, this looks very familiar to me. Didn't we just do this using u? So I'm going to just write it as 1/8 of 4r square plus 1 to the power of 3/2 times 2/3. I skip steps, that's when mistakes happen. So 1/8 times 2/3. Because of the u equal to 4r square plus 1. Now you can use u. Okay. All right, this part is 2 pi. And this is going to be between the limits of 1 to 2. So 2 pi times 2 is 4 pi over 24 is pi over 6 times 2 square is 4, 4 times 4 is 16 plus 1 is 17 to the power of 3/2 minus 1 to the 3/2. So here it is 17 to the 3/2. All right, so that is the only part that I'm not really expecting you to study for tomorrow's test. Okay? And it's nothing really complicated there, but I don't want to force you to newer things on the last day. All right, so that finishes chapter 3. Okay, now the floor is open for questions for test number 2. Do you want me to go over any examples or any concepts or anything you might find useful, others might find useful, maybe others are expecting you to say something, So just, yes.
Go through quickly, like things that we can look for to know between, like which kind of integration.
Kind of put me in a spot there, but let me see, without giving away too much. Okay. So the question was, what kind of integration to expect? You won't be doing anything beyond substitution. If that is not what you asked, though, right?
No.
Okay.
So, like you said, if we ever see x squared plus y.
Oh, yeah. So if you see x squared plus y square and not a z square, x squared plus y square, these should be pretty much set in stone. Okay. I'm trying to think if there's something that so legal statements, right? Okay, so if you see this, okay, 99.99, just like the bacteriologists say, % of the times, this is going to be cylindrical coordinates. We're talking about R3 now. Okay. And this will be spherical coordinates. Okay, so I mean, if somebody wants you to put in a terrible situation, they could by putting a couple of cylinders and then putting this as a density. can that happen? Of course, that can happen. In that case, the cylindrical coordinates won't be a bad idea because they're cylinders anyway. But in general, if you have these two, I think it's a safe way to adopt these two paths here. Okay, it's pretty safe. So other things, if you have a sphere and a cone, or just one sphere, of course, that should be obvious. Okay. Or two spheres, you cannot have more than two spheres. What would you use? Cylindrical or spherical? Trick question, right? I mean, which one? Spherical coordinates is better if you want to do it faster. Okay. In theory, all three of them will work, but then XYZ is going to be a nightmare. Cylindrical coordinates might be harder. Okay. This is better or best. But if you have a cylinder and a cone, or cylinders, paraboloids, they say whenever I have paraboloids as a plural, that means one of them is facing down, the other one is facing up. Okay. Otherwise, it cannot really trap a solid inside. And so this, and a hemisphere and a plane, a flat plane. Anytime there's a flat plane with some of the curved surfaces like a paraboloid or a hemisphere, in all these cases, it's usually easier to use cylindrical coordinates. The only overriding thing there could be this thing. Okay? If there's a density that looks like that, you probably might want to use spherical coordinates because, can I try to not put you in a terrible spot by making it too confusing? It should be pretty straightforward based on what we have practiced so far. But you should only be doing one of each tomorrow. If you do two of any one of them tomorrow, that was not what I expected. Okay, not that you're wrong. If you do two spherical coordinates tomorrow, one of them may be at the wrong place. Just it's a hint. All right. Any other examples or anything that you want me to go over? Just pick anything from anywhere. All right, so let me see if I can pull out some much older final exams and ask you for your opinions. Yeah.
Sort of related to the quick one.
Uh-huh.
If you were doing spherical, the density is x squared plus y squared plus z squared.
Yeah.
You would end up integrating rho to the fourth sine squared.
Yes, because this is rho square, and then there's a rho square in the dv. So yeah. Yeah, so let me try to look at some older final exams which I did not post, and then see if I can do some of those here. And Alrighty. Okay, so here is a pretty good one just to practice. I'm gonna pull the screen down, and I'll also share the screen for those of you who are online. That is the one that we once did, I think, but this one here, number 9, kind of covering up the answer as much as I can. So, And let me share the screen for those of you who are online. Hold on one second. The screen, this one, this. So problem 9. Okay, that's what I'm. Oops, I don't want you to see the answer too early. This one, number 9. Okay. Please make sure that you write down all the details. Okay, there are lots of things in there. So you have above the XY plane, which is part of the first octant, below the cone. Okay, usually we do above the cone, outside of the sphere of radius 1, inside of the sphere of radius 2, and the density is given by this. Zoom in. Oh, let me see. Yes, I think it should be. Is that better?
Are we looking at 8 or
9. 8 is kind of a silly one.
9? Sorry?
8 is kind of too easy. 9. I'm looking at 9.
I can't read either. I'm sorry. I have trouble eyesight too.
Oh, really? This one. Should I zoom it in even more?
Could you please?
Sure. Is that better?
Thanks.
Can people online see it? Okay. Desperately trying to cover up the answer, but this was, I think, for 2016 final exam. I think so. Maybe it's possible that none of you even knew what integrals were at that time. Then we are doing number 9. Okay. All of you took down the problem. This is 1 over x squared plus y squared plus z squared. Okay. Okay, so try it first and see what happens. Can I stop sharing for the people online, or are you still? Might have to either take a picture of it or write it down. Okay. Let me know if you want me to project it up again and put it up. Do you have all the details, or do you want? Not yet. Let's see. This one.
We're not confined to the first octave, right?
We are not confined to the first octant, but we are confined to above the XY plane. So it's part of the first octant, but not completely confined. Everybody finished copying the question? All of you? All right, so take a few, just set it up, okay? I mean, the computation part is something you could do later yourself. Yeah, and this is probably a little bit annoying. I won't make it this annoying, but yeah, the level of difficulty is. Yeah, I will tell you why it's annoying. Okay. That number 2 there in the cone is a little annoying. About XY plane. Below this, okay? Don't miss any words there. Two. I hope all of you agree that spherical coordinates is a good idea for this. Yep. Yeah. Both sides. So it's kind of going around. So can somebody quickly tell me the limits for rho here? That's the easiest. Oh, yeah. Just 1 to 2. Okay. So if you don't panic, a lot of things in this question are pretty easy. And this is 1 over rho square. Okay. This is also easy. What are the limits for theta here? 0 to 2 pi. Okay. A lot of things are just straightforward things because we are not in the first octant, and so the value of theta is not going to change. So the only tricky part is what is the angle phi doing here? Okay. Don't forget phi starts from the North Pole. So the question is what is phi here and what is phi here? Okay. This part. So this is your phi start and this is phi end. What is phi end here? Where does it? Pi over 2, that's the equator. Okay. What about phi start? Oh, is it really?
Arctan.
Oh, really? I didn't know that. I didn't know it had a perfect pi over. If that is, that would be nice, but.
I don't know, it was like the decimal was like 0.14. I thought it was 1.7.
Oh, okay. So anyway, so let's do this. So this is rho cosine phi equal to 2 times rho sine phi. This is what you would do if you get a unfamiliar cone. Okay, just set those two equal to each other and don't do things that I did yesterday. Okay, just take it slowly, cancel the rho on both sides. So you get sine phi over cosine phi equal to 1/2. So 2 sine phi equal to cosine phi. Okay. So tangent of phi equal to 1/2 of phi would be the arc tangent of 1/2. This is why I said it's a little bit annoying because you have to write this angle in radians, okay, which could be close to pi over 7. You said,
Yeah, it's a little bit greater.
yeah, I don't think that's exactly. I mean, people would have found that out by now if it is. But let's take. Can you calculate and tell me what that is?
It's 0.464
All
approximately.
right, yeah, 0.464 in radians. Okay, so just make sure that you don't write any degree measure angle. So 0.464. Okay, that is this value here. That's the only creature you have to deal with here. Everything else is pretty straightforward. Okay, so you deal with any of those not so famous cones. Just do this. So the mass would be the triple integral of the density. That's going to be 1 over rho square times rho square sine phi d rho d phi d theta. And since I'm doing rho first, that goes from 1 to 2. Can cancel the rho square actually, so it was nicely designed for you. Phi goes from this rather unsavory number 0.464 to pi over 2, and theta goes from 0 to 2 pi. You almost made me run to the math department and tell them that it was pi over 7. You know, people would have been excited. All right, so if you look, I think if you do this answer, you will get around 5.619. You know, just do this at your convenience and leisure. Okay. I don't expect you to write the units, but since the problem was given in kilograms per meter cube, okay, it's kilograms. That is if you plug in all the pi and everything into it. But are you okay with the reasoning behind the limits of integration here? Any questions? All right, what about people online? All of you okay? You want another one? Why not? So I think I figured out a way to just project the question so that way I don't have to keep hiding the answer with me. I know this might look a little weird, but it's actually one of the final exam questions. Okay. We want to zoom it in further. There you go. And zoom, people, zoom. Share screen. There you go. This is from fall 2015. Okay. Why do these things? It's a very distracting question in a summer day, right? Actually, if you log into Zoom in the here, you can see this on the screen. It's okay. You don't have to write about the ice cream and all that, kids. Everybody has it here? Then I'm going to stop sharing. All right. Again, just set up, okay. Okay, so if you know the cost per pound and the density, that is mass per volume, how do you find the cost?
Calculate the mass of the cone, taking triple integral of that 0.04 over the entire solid times the $2.
Okay, so it's just, so the total cost would be $2 per pound times 0.04, which is pounds per cubic inch times the volume of the solid. Okay. The good thing here is that both the cost and density are numbers, so it's not going to factor into your integration. You can do the volume peacefully here. Okay. Alrighty, now let's listen to the limits of integration here. Let's start with the easy ones. I wrote 0 there already. Okay, what is the upper limit for the rho here? 5. It's a sphere of radius 5. Okay. What about theta? 2 pi. Once again, we are assuming that spherical coordinates is best here. Okay, so 2 pi is because of that circular cross section there. Okay. What about phi? Now we are starting again from the North Pole and stopping at this cone, okay, this angle. This is phi equal to 0. This is the one that I messed up yesterday. This is phi equal to 506. Okay. Don't forget that this is the same as writing square root of 3 times the square root of x square plus y square. That's the same thing. Such minor algebraic adjustments are expected, so phi is pi over 6. All right, so the total cost would be 0.08 times the triple integral of 1 rho square sine phi d rho d phi d theta. And since I kept this order of variables, your rho goes from 0 to 5, phi goes from 0 to pi over 6, and theta goes from 0 to 2 pi. And you can do that integral yourself at your convenience, and the answer at the end, if you just do all the calculations, comes out to be $2.81. Okay. Which makes sense for an ice cream. All right, so that was the for 2015. Let me see if there is anything interesting here. I think if you're looking for a really hard one, here is one. Okay. Just for a variety. I won't push you to this limits tomorrow, but just to do a few. So there is a region which is inside a hemisphere and also outside the cylinder. Yeah. It's a rather tricky situation, cylindrical or spherical, but then you see the density, you probably want to stick with spherical coordinates. So try that. This is probably one of the harder final exam questions. So from 2014. So depends on who writes the questions each year. The z greater than or equal to 0 is the upper half plane, okay, above the xy plane.
Professor, do you mind sharing your
Oh,
screen?
sorry, my bad.
Thank you.
I'm just, I was looking here. I'm terribly sorry about that. Okay. Yeah, I didn't mean to exclude you people. Okay. So you get some extra time to work on it. Are all of you done writing the question here in the classroom? So once again, there is no lecture tomorrow. Okay, so wherever you are, just find a quiet space and write your test. If you study ahead of time, it should be pretty easy. If you're planning to watch videos during the test, it's a different question. Once again, it's just to set up. Okay, and I would suggest that you start thinking about spherical coordinates here because of the density. Okay. All right, is everybody done copying the question? Can I stop sharing? So write down the equations of the sphere, cylinder, z greater than or equal to 0, and the density. That's the main part of the problem. Okay. Let me know if you want me to share it again. I can put it up. Draw a picture because it's a little strange. So there is a cylinder which is sitting inside the sphere. Okay. And you're concerned about the volume which is outside this. And it's still centered at the origin, so it goes like this. Oh, you mean this gap here? Yeah, everything that. My pictures are always a little bit crude, you know. So X, Y, Z. Why would what? It's outside the cylinder and inside the sphere, so there might be a little gap there, right?
There's no plane that like dictates the upper limit of the x. There's no Like, doesn't the cylinder just extend directly upwards?
So this is sitting, oh, you mean sitting like this?
Yeah.
I have to look at what the question says here. Let me just see. Consider a solid that lies inside the hemisphere. Oh, I see. Inside x square plus y square plus z square equal to 4. And outside the cylinder, which means that you're just keeping the sphere here and there's nothing in between. That's, yeah. So the cylinder just goes into the sphere as though you're just inserting it using a hammer or something. Okay. And there is some space out here, some space out here. And this is x square plus y square equal to 3. The cylinder. Okay. So we had a similar situation yesterday, right? You're trying to write a flat thing in terms of spherical coordinates. It's always a challenge. Okay. So the inside radius is the distance from the center to the edge of the cylinder. The outer one is easy. That is the one that goes into the hemisphere. Okay. So the row in or the row inside would be the radius of the cylinder expressed as rho. The hemisphere is natural. Okay. So rho min less than or equal to rho less than or equal to rho max. This is given by 2. Okay. Rho min is the distance from the center to the edge of the cylinder. Okay. How do you find that? It has to depend on phi. Okay, remember how we did that flat plane yesterday? This is what you have to keep in mind. R equal to rho sine phi. In this case, what is R? Plus y square. Okay, so that is 3. So what is this is R square. So what is R? Square root of 3 equal to rho sine phi. So rho is going to be square root of 3 over sine phi. You cannot escape this because you are trying to write a flat thing in terms of spherical coordinates. Something has to give. Okay. So this is going to be square root of 3 over sine phi.
So if you were to draw a triangle using rho as the hypotenuse, phi is the angle of the triangle, what would that height be? Because I know that's the lower bound of rho, right?
The lower bound of rho would be the distance from here to here. Yeah.
Okay, so what would the height of that right triangle be? I'm trying to like see it jump.
That would change with the angle phi though, right? Depending on where you are, there is no fixed value there. That is an ever-changing height.
We're fixing it where the cylinder and the sphere meet.
Oh, yeah, that's what we're going to do next. So one, if you're talking about the meeting point, that's the next thing we
So
have
we
to.
don't need that to calculate the lower bound of rho.
No, the lower bound of rho, it just keeps changing from the center to this line here. So if it was a flat plane like this, you would do z equal to rho cosine phi. That is what we did yesterday, right? Here it's a vertical line. That's why you have this r based on the radius of the cylinder. Okay, so that is rho sine phi. Either way, there has to be some kind of a weird limit here because of the cylinder sitting inside a sphere. And when they intersect, what happens? When the cylinder meets the sphere. Sounds very poetic. That is this part here. now we are talking about the same situation like we had yesterday. We had that hemisphere meeting that flat plane yesterday, right? That is when the two things are equal. So you have the r, which is square root of 3 over sine phi, and that becomes equal to 2. Okay, that is where the two radii are the same. Okay. These two limits would be the same. Square root of 3 over sine phi, which is the radius based on the cylinder, and the radius of the hemisphere, which is 2. That will be this angle here. That is the intersection point of the cylinder and the sphere. Now, that is a clean angle actually. So sine of phi is square root of 3 over 2. What is phi? Pi over 3. 60 degrees, right? So it starts in the North Pole and stops at the point where the cylinder and sphere are just meeting. Okay, that is when the two bounds of the radius are the same. And what about the angle theta here? So 2 pi. Okay. Whole thing always stays the same unless you are the first quadrant. Oh, yeah. So the volume, was it a volume or a mass question? I forgot. Mass. Okay. So the density was what? Okay, 1 over rho square. Yeah, but, if not for this, I would have stuck with cylindrical coordinates. That would have been easier. This reason why I'm doing spherical coordinates. So the mass would be 1 over rho square sine phi d rho d phi d theta. Okay, and the lower bounds for rho would be square root of 3 over sine phi to 2 phi from 0 to pi over 6. This has to be done first. Okay, the d rho limits must be done first. 0 to pi over 3 and 0 to 2 pi. Where is the picture? Oh, we're talking about the region which is between those two. Yes, pi over 3 to pi over 2. Shouldn't be taking my eyes off the picture. Okay. Because you're starting from the cylinder to the edge of this hemisphere. Okay, this part here. So this is phi equal to pi over 3 to phi equal to pi over 2. Picture is the key.
So just to reiterate how you found rho min. So rho is the hypotenuse, and that's ever changing, right? Depending on phi.
Yeah.
And so the base of that triangle, I messed up when I said the height. I meant the
Oh, base. Okay.
R, so that's x squared plus y squared.
Right.
And so that's root 3.
Yes.
Okay.
Yeah. Yeah. When you said the hypotenuse, that kind of keeps changing there. The base is the radius on the xy plane. That is given by root 3. Okay. And since this is just a vertical line, spherical coordinates won't fit in there. That's why we have a changing rho here.
Say it was just find the volume, we didn't have the density function. How would we set it up for cylindrical?
Cylindrical coordinates would be for the same problem.
Yes.
So you have r square plus z square equal to 4, right? Because that's r square. So z would be plus or minus the square root of 4 minus r square. Yeah. Now, if the problem says it's greater than or equal to 0, you don't have to start from the negative part, right? So it'll be 0 less than or equal to z less than or equal to square root of 4 minus r square. That will be the height of the solid. And then the radius and the angle would come from the cylinder. So rho less than or equal to r less than or equal to square root of 3. And all this hassle was created by that density term. Yeah. And you don't want to deal with the density in cylindrical coordinates. That's a headache. All right, I think it's 11:30, so let's call it a day. I have office hours at 12:10. Okay, and feel free to stop by if you have any additional questions. This is probably the extreme case of spherical coordinates. I won't ask something like this tomorrow. Okay, that's too much for a summer course. I'll keep things pretty nice and easy. The previous two examples are pretty good. The ice cream cone and the one above it. Okay. So just I'm expecting very nice and easy working problems tomorrow. So don't complicate things. And I'll be online during the test time. If you have any questions, just email me. All right then. So no lecture tomorrow. I'll see you on Monday. Some exciting things coming up next week. So get some rest during the weekend. Okay. We'll start vector calculus next week. All right. Let me stop recording. No, the vector calculus. Well, we haven't done vector and calculus at the same time. We either did vectors or calculus.